The purpose of this lab was to capture an object dropped from rest and falling in a downward motion. I then analyzed this video in Tracker and Python. Newton's second law was the fundamental principle of this movement and was used to predict the final velocity. Newton's first law was also a key principle in this lab. It states that an object in motion acts uniformly until acted on by another force. In this case, there are other forces that act on the object, the force of gravity and drag force. There is not constant velocity in this lab because there are forces acting on the system. The kinematics, or displacement equation, is also used to know the final position of the object. For this video, I dropped a crumpled up piece of paper and uploaded it into Tracker to analyze the video. First, I calibrated the video using the diameter of the paper ball, which was 0.0635 meters. Then I made my coordinate system. The ball is moving in the negative y direction on the axis. The initial position of the ball is at negative 0.008 in the y direction, so I noted this for when writing the code. I also tilted the axis some so the ball is falling on the axis. I then tracked the center of the ball in each frame to find the position of the paper ball. Moving on to Python, I made a computational model only accounting for the force of gravity. I changed the initial condition so the ball was the correct mass, 0.00142 kilograms, and the initial position of the ball was at negative 0.008 meters in the y direction. Notice that Newton's second law and the displacement equation did not have to be changed. Also, I had to set g, the gravity, equal to 9.8 and j hat equal to 0.10. These constants are used to calculate the force of gravity weight, which is symbolized with the W and set equal to the negative mass of the ball times g times j hat. The model was ran and graphed with the observed motion of the ball. Notice the model is a good fit in the beginning when the velocity is fairly constant, but as soon as the paper ball speeds up, the velocity overcomes the force of gravity. There is obviously another force acting on the paper ball and slowing it down. Therefore, I ran the model again, taking the force of gravity and the drag force, which is the same thing as air resistance, into account. The equation for drag force is negative b times velocity. I needed to find a b that would satisfy the movement of the paper ball. I found this using the final y value and experimented until 0.00385 gave me a y value very close to the actual value. I also changed the net force so it included the force of gravity and the drag force. I then ran the program for a computational model and graphed all the data in Excel. Accounting for gravity makes the model fit the actual data much better. The paper ball slows down due to gravity and the drag force. The ball continues to increase in velocity, as you can see by the curve, but the forces make the ball speed up at a slower rate. The model is a little off during the middle of the graph. This could be the result of an error when making assumptions about the forces acting on the paper ball, such as a slightly off b value. Terminal velocity of a falling body takes place when the object experiences zero acceleration. This is shown by the second model where drag and gravity are accounted for because there is little or no change in velocity after a while and terminal velocity is reached. If the paper ball was thrown down instead of dropped, as can be seen here, using an initial velocity of negative 10 meters per second, the drag force would have exceeded gravity. The ball would decelerate in the beginning and the F net will become 0 and the terminal velocity would eventually be reached.